All right, so now we continue on to lesson 6.3, adding and subtracting rational expressions, and we move into part 2 where we're going to deal with more of these denominators that are binomials or are in factored form. In the previous lesson, as mentioned, we dealt with primarily monomials and trying to figure out how do we establish a common denominator or an LCD given that it's a monomial. In this case, we're just going to move more into the binomials and the factored form. Now, again, we're going to start off with determining the sum or difference given a certain overall statement or rational expression, and we want to write it in its simplest form, making sure we identify non-permissible values. Now, the steps are going to follow all the exact same. We're going to state our NPVs once we've factored, so maybe we should start with that. We factor it, state the NPVs, then simplify once we establish the LCD. Okay, let's look at the first example here. I see A and I'm looking at this and I'm like, okay, well, there's two rational expressions added together. What I want to do here is I want to write this as, we're going to try to factor this a little bit further. So I'm going to write equals. In the first fraction, I can write this as 4 over. I recognize this is a difference of squares, so I'm going to write it as p plus, and let's just make sure I got this. So p plus 1, and then my x1 is p minus 1. There we go, because p squared minus 1 is a difference of squares where we can plus or minus their squares. Plus, in the other one, we're going to write this as 3 divided by our first binomial is p plus 1, and then our second one is p squared plus 1. Now, unfortunately, there's no such thing as an addition of squares, so we can't form two binomials out of this one. What we're going to have to do is just continue forward and say, okay, at this point, let's establish our non-permissible values. Our non-permissible values from here, just like we did in our previous part, or part number 1, I'm going to just write them up to the top here. So I'm going to go NPV, and then we're going to write where p cannot equal. Now, in this situation, it can't equal plus or minus 1, and that accounts for all of them because in the first two, we see if it was plus or minus 1, it would eliminate that to 0. If it was negative 1, here it'd be 0. And then here, regardless if it's plus or minus 1, it's not going to go to 0, so we don't really need to worry about this one necessarily. It's just these other three that we have to be concerned with. So as long as we put plus or minus 1, we are happy with this. Now, let's continue with our LCD here. So we're going to write it as our lowest common denominator, or LCD, is going to be the following. And maybe I should shuffle this over just in case we need the space. Our LCD is going to be the following. It's p plus 1, p minus 1, and then p squared plus 1. Now, why is it all three of these binomials? Because if we look at the denominators, they both share p plus 1, so we're happy with that. But one of them has p minus 1, the other one has p squared plus 1. In order for them all to match, we need them to have all three of them. So that's kind of an easy way to analytically look at this and decide what we're going to multiply it by. Now what I'm going to do is I'm going to multiply each side by this given term, or the missing terms, I should say. So I'm going to write this as, and I'll give it a little bit of space out in front. We're going to try to manage our space as best as possible. This is p plus 1, p minus 1. In the second fraction, I'm going to leave a little bit of space again, and we're going to write this as our p plus 1 and p squared plus 1. There we go. And just to make sure we're not interfering with our other problem too much, yeah, it seems okay from here. Okay, what we're going to do is we're going to multiply the first fraction, and I might have to move this equal sign just over a tad just to give us a little bit more space. I need to multiply by the thing that's missing here. The thing that's missing in the denominator is the p squared plus 1. So I'm going to write this as, let's multiply this by p squared plus 1 in brackets. As such, this will also be p squared plus 1 because we need to multiply it to the numerator and denominator. In the second fraction, we realize the missing term is the p minus 1. So we're going to multiply this by p minus 1 and p minus 1. And when we multiply these to numerator and denominator, therefore we're going to create that LCD and we can combine the terms. So let's do that in the next step here. This is going to be equal to, in the numerator of the first fraction, this is going to be 4 times p squared, which is 4p squared, plus 1 times 4 is 4. And then we move to our second one, p times 3 is 3p. And then negative 1 times 3 is negative 3. Now we can divide this all by the common LCD. Our common LCD was p plus 1, p minus 1, and then finally p squared plus 1. Awesome. Okay, now once we have it here, let's just collect our like terms, and then we could probably just end off at that, unless we can factor it further, but it might not be possible to factor it further. So we're going to write this, maybe I'll just do it off onto the right-hand side here. We're going to write this as equal to, for this one, p squared terms, it looks like we only have the 4p squared. In terms of p's, we only have 3p, so I'm going to combine those together. And then in terms of the numbers, 4 minus 3 gives us positive 1, and then we're going to divide this all by the p plus 1, p minus 1, and then the p squared plus 1, which was our third term. Now, we just want to double check and we want to see if we can factor the numerator just in case. So I look at it at this point and I go, well, multiplies to make 4, but then adds to make positive 3. Is there anything that does this? And in fact, unless it would be complicated factors, probably not, because in this situation, if you think about things that multiply to make 4, 4 and 1, 2 and 2, none of them are going to add to make 3. So we can't just easily put this into factored form. Therefore, I would end it here. As long as you have your simplified trinomial, and you have your LCD stated in the denominator here, and it's all over this with the collected like terms, we're like good. And again, you want to keep it in its factored form if possible. So if the numerator could easily factor, you'd want to make sure you factor it and then potentially cancel if you can. But at this stage, we would be happy with this. So those 3 steps, again, look very, very similar to our previous lesson. We're like, okay, factor it, state the NPVs, state the LCDs so that you understand what you need to figure out or what you need to make in order to make the denominator the same. And then from there, you can simplify it. Okay, let's move on to part B, which is very similar, maybe a little bit easier because the factored form is slightly easier. Right away, we're going to factor this thing. So we're going to go is equal to in the denominator. I'm going to factor this to be 2 on the outside and a minus 7 because I can divide both terms by 2. Then I'm going to go minus 2 over 3a plus 3. Well, I can take out a 3 and leave this with a plus 1. All right, now we want to state our NPVs, so we'll do that off on the top hand side here, or on the right hand side. Our NPV is where a cannot equal, well, the 2 situations in which a cannot equal, one of them is going to be positive 7, so I'm going to write positive 7 here. The other one is going to be negative 1. If a is equal to 7 or negative 1, it's going to wipe out those denominators. We don't want that to happen. Okay, now what we want to be thinking about is the LCD. So we're going to write that below here, and we're going to be like, LCD, well, numerically, if we look at this, we have 3 and 2. What's the first number 3 and 2 multiplied to? It's 6. So we definitely want a number that will be 6 for our denominator in terms of the numeric value or the numeric coefficient. And then in terms of the other part, it's going to be the a plus 1 and a minus 7 because we want it to match in terms of the binomials that are existing there. So let's create our little template below here just so that we can establish what we're going to have to multiply each by. I'm going to leave a bit of space out in front just like I normally do. And I'm going to write this as 5 divided by, we had 2a minus 7. For my other one, we're going to go minus, leave space again, and we're going to make sure we put our numerator of 2 and then divide it by 3a plus 1. Okay, now in these gaps, we need to fill in what we need to multiply by to get it to the LCD. So I'm going to go multiply by, I'm going to create a fraction, and then I'm like, okay, well, if I want to multiply 2 to 6, I need to multiply them both by 3. So I'm going to put a 3 and a 3. If I want a plus 1 to exist here, well, I have to fill in the a plus 1 here as well, such that when we multiply this, it's going to add a plus 1 to the denominator. Now, very similarly, if we go over to our second part here, this is, we have an a plus 1 already, we have 3. To make 3 go to 6, we multiply both by 2, and we realize a minus 7 is the missing binomial, so I'm going to multiply both the numerator and denominator by a minus 7. Now from here, let's make sure we establish the term as one single fraction or one single rational expression, and then we're also going to multiply the terms through. So I'm going to kind of do 2 things at one time here. I'm going to multiply the 3 in, and then I'm going to also multiply by 5. So if we go 3 times a, that's 3a, multiplied by 5, that's going to give us 15a. I'm then going to go 3 times 1, which is 3, times 5, which is 15. I'm going to add 15 here. Okay, now we're going to minus because of the subtraction that's here. I'm going to go 2 times a is 2a, times 2 is 4a. So this is negative 4a. Okay, then I'm going to go 2 times negative 7 is negative 14. Negative 14 times 2 is negative 28, but because the negative here, it's going to be positive 28. There we go. All right, now in the denominator, we're just going to put this as one fraction and one LCD. We're going to write this out front as 2 times 3 because the 2 times 3 for both of them in terms of 3 and 2 being combined together will give us 6. Then we can put a plus 1 and a minus 7. Now, if you put the a minus 7 before the a plus 1, that's totally fine. In fact, the order will not matter here. The most important thing is that you just have the actual factors themselves. So you could even put 6 on the back if you wanted, or you could put it in the middle if you wanted. I mean, either way, you could put the a plus 1 first, you could put it last. It really doesn't matter because in multiplication, the order in which you multiply the items doesn't really matter. Now, in the case of this, it's going to simplify to 15a minus 4a is going to be 11a. We then have 15 plus 28. Well, if we add 10 and 20, we get 30. We add the 5 to the 8. This is going to give us, I believe it's going to be 43. So we're going to go plus 43. and then all divided by, in the denominator, 6, a plus 1, and then a minus 7. Awesome. So there's our final term. Now, can we do anything more with this? No, because at this point we see it as, hey, you know what? There's really nothing we can take out as a common factor. We can't factor the numerator anymore, and we can't cancel any of the terms out. So we look at this and we're like, you know what? This is great. Satisfied the problem, so I'm happy with this. Okay, let's move on to part B. Part B, we look at this one, another one where the factors are going to be quite simple, but we're going to do something we've done earlier in this unit that you may have forgotten that we did. When I see it as this 3 minus a, if I want to make the a go before the 3, I can just take out a negative. So what I'm going to do in both of these is I'm going to look at this and be like, well, I can write this as 1 over, and if I want to factor this so that the a goes first, I'm just going to write it as a minus 3, but I'm going to remove a negative out front such that it maintains the same terms and their ordering technically, but it just reformats it so it will match what we're going to do for our second part. For this one, once I do this, I'm going to write this as, well, a squared minus 9. This gives us a difference of squares of a plus 3 and a minus 3. And again, the reason I did that first step, or I did this with the first rational expression, is I wanted it to match the one from over here. So when we do our LCD, it's a little easier. Same with non-permissible values, I guess, but you know. All right, so now we're going to go MPVs. A cannot equal, because in this situation, instead of x's, we have a's. It's going to be plus or minus 3. If it's plus or minus 3, that's going to take away these denominators, and we don't want to have that because then, you know, it's going to create undefined functions or undefined fractions, which we don't want. All right, now from here, we're going to state our LCD, so lowest common denominator. Well, if we look at it numerically, we have a 1 technically here, because there's always that invisible 1. We also have an invisible 1 here, but it's negative. So in terms of the number here, we want to write it as -1 as the LCD for the numeric value. For the overall terms here, we're going to have a plus 3 and a minus 3 because we want one of each of them, and that will help us create the lowest common denominator. So our lowest common denominator is negative, a plus 3, a minus 3. Now, in order to do this, let's just make sure we create our template here. So I'm going to write equals. I'm going to create a little bit of space. So I'm going to go 1 over, and then I'm going to put negative a minus 3. And then I'm going to go plus. Again, I'm going to leave a bit of space here and then put the 1 over the a plus 3 and a minus 3. There we go. I know it's a little bit squishy, but we're going to try and make this work here. Now from here, I'm going to go multiplied by. In the first sense here, well, I'm missing the a plus 3, so I know I need to put that there. And I think that's the only thing I'm missing, so I'm just going to make sure I write a plus 3 and a plus 3 in the numerator and denominator. Perfect. Over here, we realize that only the -1 is missing. So ideally, what we can do is we could even shift this over, but you know what? I'm just going to keep it as is. I'm just going to multiply the negative here. Okay. Now from here, I know that our other problem kind of interfered with here, but I don't think we're going to need much space for the next step. We're going to multiply in our numerators. So we're going to multiply this 1 to each of these. Well, 1 to each of these is just going to keep them the same. So it'll be a plus 3. And then we're going to go plus. On the other part here, we see this as 1 times -1. Well, instead of putting a plus, because it's just going to be a -1, we can write -1 here. And this is all going to be divided by the following terms. We have a -1 in the denominator, we have a plus 3, and we have a minus 3. Awesome. Okay, let's simplify our numerator here. So this is going to be equal to a plus 2, and then all divided by, we have the negative, and instead of putting -1, I'm just going to put a negative there now. A plus 3 and a minus 3. And that wraps up this problem here. And again, if we could do anything more with this, maybe we would, or you know, if we could factor any of the terms more or cancel any of the terms, we would. But at this situation, we see this as a fully simplified rational expression, and we are happy with this solution. Now, again, like with most mathematicians, they see a -1 here, and you know, if you put -1 there, you're not going to lose marks because it's technically correct. But in math texts or any sort of formalized math, often if it's a 1 there, they're just going to put the negative there and leave it at that. So that's why I summarized our answer without a 1 there, just because it's not super common to put that in as a 1 in terms of formalized math. Okay, let's zoom out, just make sure everything's neat on those first two. Perfect, okay. Now we're going to go to D. So with part D, this one's going to require probably the most amount of factoring that we've done to this point. What you can do is you can take these trinomials and you can factor them off in the margin and then continue, or if they're easy enough, in this case they're by inspection, you can just do them directly in the problem. So that's exactly what we're going to do. If they involve decomp, I might take them off to the side, but I mean, for this situation, I'm just going to keep them within. This is going to be equal to, I'm going to put x minus 1 in the numerator, divided by, in the denominator, we need a term that multiplies to make -6, but then adds to make +1. The two terms that can do that for me are a plus 3, or not a, but x plus 3. And then in our next one, it's going to be a minus 2. And I keep saying a just because of the previous part, but no problem. X minus 2, x plus 3. All right, now we're going to subtract away. In the numerator of this one, we have x minus 2 all over. We need to multiply to make +3, add to make 4. The two terms that can do this for me are going to be x plus 3. And I keep putting a's, but that just bleed over from the last one. X plus 3, x plus 1. If we can put those two, good. And it's what, realistically, you could sub in any variable you want here. So if you made this problem out of a's, I'd be like, it is what it is. Like, variables are just substitutable values. So it's not going to be the end of the world. It's just make sure if you put in an a here, or if you put in a z here, it goes for all of them. But side tangent there. Okay, now we're going to do our non-permissible values because we've factored it at this point. So x cannot equal, and in this situation, we have it where x cannot equal -3, or else that would go to 0. Same thing for here. If x equals +2, it would go away, and if x equals -1, it would go away. So let's just list those out here. So we have -3, we have +2, and then the last one was -1. If it is any of those values, it's going to wipe out these denominators, and we don't want to have that happen. So these are the non-permissible values. We cannot go this way. Now let's state our LCD below here. So we're going to go LCD. And in terms of numeric value, there's no sort of coefficient here, so we're good with that. We know that it has to have an x plus 3 for sure. It must have an x minus 2 because that's one of the factors, and then it must have an x plus 1. As long as it has each of these factors, we're happy because then they'll share the same denominator. Now let's create our template here. So I'm going to go, let's just double check our space here because I don't want to go too much over into the next problem. This is equal to, we're going to leave a bit of space and then put our terms. So I'm going to put x minus 1 and then divide it by our x plus 3 and x minus 2. I'm then going to go subtract. I'm going to leave a bit of space. So I'm going to put x minus 2 divided by, in this denominator, our x plus 3 and x plus 1. There we go. And then in the gaps of the front here, I'm just going to put the missing term. So for the first one, we see that it has x plus 3, x minus 2, meaning it's missing the x plus 1. I'm going to put that for numerator and denominator. And then for the second term here, we need to make sure that it has the x minus 2. So I'm going to write x minus 2 and x minus 2. Awesome. Okay, now again, why are we multiplying it to numerator and denominator, numerator to denominator? Just like in 6.3 part 1, I told you guys, it's so important to put this in the numerator and denominator and not just write it out as a one-time thing like, oh, forget about this part here, just write x minus 2. This implies to any formalized mathematician that you're just multiplying it to the numerator, and that's not what we're doing. In fact, this needs to be something that could cancel out and make 1, which in this case it does. If you only write it in one position, you're telling me that you're only multiplying it to one spot, which is actually totally altering the terms, and it's not maintaining the equality of the rational expression. Now, from here, we're going to multiply this through. So I'm going to provide some steps here, or kind of truncate some steps. If I multiply two things that are conjugates of one another, it means the middle term goes away. I can rewrite this as x squared minus 1. And in fact, we know this is a difference of squares. X plus 1, x minus 1 should give us this difference of squares. Then I'm going to go minus, and we're going to put the expansion of the right-hand side here. X minus 2, x minus 2, well, they're the same thing. It's a perfect square trinomial. I'm going to write it as the following, and then I'll distribute the negative after. It's going to be x squared minus 4x, and then plus 4 on the end. And I'm keeping it all in brackets because I'm going to distribute this negative afterwards. Now let's write our LCD here. Our LCD is x plus 1, x minus 2, and then x plus 3. And again, who cares about the order in which these are multiplied? It doesn't really matter. They're all right. Now from here, this is going to be equal to x squared minus x squared is 0x squared. Negative 1 minus 4 is negative 5. And then negative minus, or I should say a negative minus 4x, that's double negative becomes a positive. This is going to give us 4x. And then for our numeric value, negative 1 minus 4 is giving us negative 5. So I'm intentionally writing it in descending order of x. Then I'm going to write in our trinomials here, or sorry, our binomials here, x minus 2 and x plus 3. There's our answer. And we can't factor the numerator anymore, so we have to live with this being our solution. As long as we've stated our MPVs, we're happy with this solution, and we think this is good here. So let's just zoom out here and recap the steps. Again, we factor it, if it's trinomials, difference of squares, whatever it is, we factor it, state the NPVs, establish the LCD, then multiply numerator and denominator by that missing term on each fraction or each rational expression, combine the numerators, leave it in its factored form, done. All right, let's go on to our final section here, which is problems that look like these. And you're probably looking at these being like, whoa, what am I even looking at? There's fractions all over the place. It's just, it's a mess. What I recommend is I'm going to show you an organization method that will actually help you do this in a very simplistic way, and show you how you can actually end up getting a solution that's a lot nicer than you might think. So if we look at this, simplify and state all the non-permissible values. I mean, right away, one of the non-permissible values that jumps out to me is that y cannot equal 0. So in a way, I'm almost like, okay, let's hold on to the idea, and maybe we'll do our MPVs right below here. We'll save them here. MPV, y cannot equal 0, because if y was 0, it would wipe out, it would make one of these fractions have a 0 in the denominator, and if these fractions have a 0 in the denominator, we don't like that. So we're going to account for that right away before we even start. Now, what we're going to do is we're going to break this apart into 2 steps. I'm going to go from here, and I'm just going to arrow over like this and say, for part number 1, which is going to be dealing with this numerator, we're going to make it have a common denominator such that it only has one denominator. So in this situation, we look at this, and it's already factored in the numerator like this, and we're like, okay, well, if it's already factored, then we're going to create the LCD. So I'm going to write it as the following: 2 minus, I'm going to leave a space, 4 over y. And you're probably looking at this and being like, okay, well, what do we have to multiply them by? Well, in this situation, if I want to create this LCD, I need to multiply this one by y divided by y. And the reason is because if I multiply this by y over y, it's then going to make this have a common denominator of that y. And the nice thing is this one already has the y in the denominator, so we're good. I'm going to write this as equal to, it's going to be 2y minus 4 all over y. Okay, so there's our common denominator. We're happy with this. We're like, great, perfect. It only has one denominator and it's a little less complicated. Now what I'm going to do for step number 2 is I'm going to repeat the exact same process just with the denominator. So I'm going to go step number 2. In this situation, again, we see a common denominator of y, meaning I'm going to have to take this y minus 4 over y, and I'm going to want to multiply that first term by y over y. Because again, if I'm trying to make this have a common denominator of y, I need to multiply numerator and denominator by y. This ends up giving me, well, y times y is y squared minus just 4 in this one here. Perfect. All right, awesome. And then this is all divided by the y that was the common denominator, or the LCD, as we've stated in previous unit. Now, at this point, once you've established them individually like this, you can put them together. So what we're going to do is I'm just going to reformat this just very slightly. So instead of formatting it like this where it's a vertical stack, what I'm going to do is I'm going to take this division piece here, or this quotient piece, and I'm going to put them side by side according to that. So I'm going to write it as this: 2y minus 4 all over y divided by, this is going to be our y squared, which is our second piece, minus 4 all over y. So now I've taken this rational expression and I've put it side by side like this. And I can even put an equals out front because this is still the same expression, just slightly retooled. Now what we want to do is we want to factor this fully. So what we're going to do is we're going to factor all of it, meaning I'm going to write this as 2y minus 2, because we factored out a common 2. I'm going to go over y divided by, in the numerator, I'm going to make this the difference of squares that it is. So this is y plus 2 and y minus 2. There we go, all over y. Now, here's where you'd want to go back to your MPVs for a second. We know from our unit in rational expressions that we need to look for rational or MPVs where we look at this denominator. And so I'll backpedal this just a little bit here. We look at this denominator, we look at this denominator, and we look at this numerator. Now, why was the reason we did that? It's because the flip that is caused by the division here. So we see this and we're like, okay, it's divided by. If I change that to multiplication in the next step, I know that these two are going to exchange places, so they're technically all part of the denominator. So let's make sure we go back to our MPV statement and let's retool this according to this. So what I'm going to do is I'm going to write MPVs, and maybe what I'll do actually here is I'm just going to kind of condense it a little bit more here, MPV. So we have where y cannot equal 0. That was our first one, right? We were happy with this because we were like, if y was 0, it would end up taking away the denominator, and we didn't like that. The other one is going to be plus or minus 2. We need to account for that plus or minus 2 that comes from this numerator here. Because again, division, when we have this double division statement or this double quotient, we need to account for all three of these positions here. And this shouldn't be super new to you. In fact, you should actually understand this being from earlier in the rational expressions unit that we talked quite significantly about this. Okay, there's our MPVs. Now what we can do is we can simplify this. And then I'm going to kind of reflect upon this problem in a way that will get you to be thinking about this a little more critically. So we're going to write equals 2 y minus 2 all over y. We're going to change this to multiplication and put the y in the numerator and the y plus 2 and y minus 2 in the denominator. Excellent. Now that we're at this stage, we can cancel terms because we've stated our MPVs. Remember, you have to state your MPVs before you cancel. Y minus 2, y minus 2, those go away. And at this point, we have the following. Our n term is going to be the following. We write equals, we have a 2 in the numerator, and that was the only thing left in the numerator, divided by the only thing left in the denominator, the y plus 2. There's our terms. There's our final answer. Done. Now, something I want you to reflect on here, which is very, very interesting about this specific problem, and if you ever see something like this again, I want you to be thinking about this in a way that will simplify your lives a little bit. Do you notice how when we did these fractions and our LCDs ended up being the same thing, y and y? If you take one rational expression and another rational expression and you divide them and they have the same LCD, you can actually just cancel these out right away. So if you wanted to, what you could have done is right as soon as you got to this step here, cancel out the y's, write it as 2y minus 4 divided by y squared minus 4, do the reciprocal, hey look, you would get the same answer. And if you don't believe me, try it out for yourself. If these LCDs remain the same, cancel these out and then just deal with the problem in terms of these two terms here. And maybe what we'll do is we'll actually just do that in the next part here, just to show that that's possible. I'm going to see if we have the same LCD, we can just cancel them because you're dividing something that will eventually just eliminate. We've stated our n non-permissible values, final solution, we're good with that. Perfect. And you know what I'm going to do is I'm just going to actually move these MPVs over off onto the right here. And the reason I'm going to move them off onto the right here is just because I want to make sure that we establish them in a very clear way and they're not just tucked off in the corner because they are a major piece of this problem. So y cannot equal 0 and then plus or minus 2. There we go. Excellent. Okay, now let's go over to part B to wrap up our lesson here. Now, again, we're going to solve this in terms of like a part 1, part 2 kind of deal here. So I'm going to look at this and be like, well, I want to create a common denominator here so that this looks a little nicer. So for part number 1, I'm going to look at this and be like, we need to multiply the 4 by something such that it matches the 1 over 3x. Well, that means we're going to have to multiply by 3x divided by 3x because we want them to be the same. Now, this is going to give us the following. 3x times 4 is 12x, and then minus 1 all over 3x. So there's our common term here. And then for number 2, we're going to do that same process where we're like, okay, I want to make sure that, whoops, and can't be on that tool. Number 2, I want to multiply the 4 by something such that it will match this 1 over 2x. Well, the situation that does this for me is if I realize that I want to have the 2x in the denominator, I just need to multiply this by 2x as well. There we go. Now, this is going to be equal to, I'm going to go 2x times 4, which is 8x plus 1, divided by that 2x that was the denominator term. Now, unfortunately, like we said in the last one was kind of nice because we could have canceled the denominators, and I'm just going to scroll up to show that again. Remember how these had the same LCD, or they were y and y? Unfortunately, with these fractions, they have a 3x and a 2x. So unless we make them look the exact same, we actually can't cancel them yet. And so it's a little bit unfortunate in this problem. I mean, I could make them into 6x each by multiplying this first fraction by 2 and then this fraction by 3. And then we could have the match and do that all from there. But instead of doing that, maybe we just put them together at this stage and we write them as that quotient, just like we did in the last one. So what I'm going to do is I'm going to look at this and be like, okay, let's rewrite the rational expression in the following way. Instead of it being a division that's vertical, I'm going to write it as 12x minus the 3x and then divided by. In the numerator, we had 8x plus 1 and then all over the 2x. Now, at this stage, this is where we would want to establish our MPVs. Very, very critical once we're at this stage. The 3 spots we look for our MPVs are the following location. Here, here, and here. Because in the division statements, it has to be this trifecta of these 3. So what I'm going to write is off to the side, my non-permissible values, they come from, well, x cannot equal 0, because if x was 0, it would wipe out the 3x and the 2x. And then in terms of that numerator term, or this one here, if I isolate for x, I'm going to find that x cannot equal -1/8. Bit of an odd value for sure, but I mean, it still is an NPV. So if x is equal to -1/8, we wipe out these terms. We got to account for that. So there's our NPV. Now what we're going to do is we're going to simplify this. I'm going to do the kiss and flip rule, or the kiss and reciprocal rule. This is over 3x. I'm going to multiply it by 2x all over the 8x plus 1. Now from here, we're going to cancel the terms that we can potentially cancel. In this situation, I don't really see much that I can do. It might actually even make sense to expand it, but I know one thing I can do right away is I can cancel out the x's. So that is definitely one piece that we can tackle. If I take out these x's, it's going to leave us with 12x minus 1 times 2. I can multiply those two together, and it's going to give me 24x minus the 2, because we're multiplying 2 to both of these. In the denominator, I'm going to multiply 3 to both of these, and it's going to become 3 times 8, which is 24x. And then in the denominator, 3 times 1 is plus 3. Now, here's where you cannot get caught. And it's going to be one of those things where it's like, I'm going to see it as at least 1 or 2 mistakes for some of you. You cannot just be like, oh, 24x and 24x, they're gone. My answer is therefore 2/3. And we're happy with that. -2/3, all good and well, and we're happy with this. No, that is not correct, because when things are being added or subtracted, you can't just selectively be like, oh, these two cancel because they're the same term. They're both attached together, and they both share this same denominator. So technically, if you wanted to rewrite this, it would be 24x divided by this, and then the -2 divided by this. They both share that denominator. So we can't just be like, oh, that's gone and all good and well. And if you don't believe me, use simpler numbers to try it, but there we go. Now, in the situation of this, realistically, all I can really do is just pull out a common factor, and it's going to kind of look funny because it's going to look like I just reverted a step here. In the numerator, I'm going to take out a 2 and leave this as 12x minus 1. In the denominator, I'm going to leave this as 3, and then this is going to be 8x plus 1. And I know that looks like I just reverted a step, but this would be the most correct answer, is leaving it in its factored form as such. So it might not make sense to expand it like I did. In fact, I almost want to just take that away and just not even put this, because if you put that in your notes, that might trip you up. So if you wrote it already, that's fine. Just keep it there. Otherwise, I'm just going to write it as this is my final solution, because I don't want you getting confused between those steps. There we go. So we've accounted for our NPVs, we've accounted for our lowest factor form, and then we've also canceled the terms appropriately. All right, at this stage, you're going to want to move into the textbook problems or any extra assigned problems that I have for you, but most likely it's going to be the textbook problems here. If you have questions, feel free to see me. Good luck with your practice.